All right, so good morning, everyone. Thanks for joining our last seminar of the CIEMAT Particle Physics Division for this season. Today, we are delighted to have Professor Leszek Roszkowski with us to give us a different perspective on the dark matter question with an added bonus at the end, I think he just told us. Professor Roszkowski is a well-known figure in the dark matter community, and he obtained his PhD at UC Davis and then held different positions at Warsaw University, at CERN, University of Michigan and Minnesota. Then as a lecturer first in the University of Lancaster and a professor at the University of Sheffield later, where he led the particle physics and cosmology group. 10 years ago, he received an award from the Foundation of Polish Science to start a new group at the National Center of Nuclear Research. And more recently, he's heading the particle astrophysics group, AstroCent. Also, I was very happy to see that he was one of the founders of the Cosmos series of conferences, which is a true reference in the cosmology conferences, even now 20 years later, which is the field I participate in mostly. His main scientific interests lie in the physics beyond the standard model and including especially particle dark matter, for which he has written many papers and reviews. And I think that will be the topic of today's talk. So thanks very much again, Leszek, for joining us, and the floor is yours. We'll have a session of questions after the talk.
Okay, many thanks. Good morning to everybody from the other side of Europe, unfortunately. And I understand that I'm mostly speaking to experimentalists, so I won't be hiding that I will be presenting still a theorist perspective on dark matter, on direct detection of dark matter, even though the subject of the seminar will be, for the most part, to report on the report that has been created at the request of APEC on direct detection of dark matter, mostly in Europe, but from a worldwide perspective. So I will mostly talk about that. However, towards the end of the seminar, I'd like to talk about the recent work we've done with my collaborators on the impact of G-minus, of the anomalous magnetic moment of the muon measurement on supersymmetric unified models, and in particular on dark matter, because A, this is, I hope, of general interest, and B, this may actually impact this dark matter. On my affiliations, indeed, I started back in Poland 10 years ago at the National Center for Nuclear Research, and 3 years ago I started a new center for particle astrophysics and science and technology, which takes most of my time building it up. Okay, so let's start. See how this works. Okay, fine. So first of all, I'm assuming everybody knows what APEC is, but maybe I should say it. Astroparticle Physics European Consortium is a body with an overarching aim of strengthening European astroparticle physics and the community engaged in this field. It's a community body, but its General Assembly, which is the highest body, has members from not only national agencies, but, for example, from ECFA and from nuclear physics, a similar body like this, and so on. So it's a very serious body that plays a big role in strengthening, in shaping the policy, the scientific policy. And we were asked to write a report with the main aims to provide an extensive review of the European experimental program in the broader context of the worldwide activities, current and planned for the next decade and beyond, to draft an inventory and perform a comparative analysis of existing planned and proposed technologies, including synergies and R&D, and provide an assessment of the current and future scientific opportunities in non-accelerated dark matter searches, as well as infrastructure over the next decade, and to formulate recommendations to APEC for the next step in direct dark matter detection over the next 10-year period. And this was a committee that is listed here. The report was accepted by APEC and put on the web. And now we've submitted it for publication, actually. But let me show you, now we'll talk more about the report now. So the committee members I've already listed, but I think it's important to note also their membership. They are members of different experiments, presenting different techniques, using different techniques, and different countries. And some theorists as well, myself sharing this whole body of 12 people. And after I accepted the invitation to do it, I realized that this is going to be an impossible body to create a report, and even more so to create recommendations, to form recommendations from such a diverse body of competing interests, or of people representing competing interests. Nevertheless, the report was prepared, and actually in a rather amicable atmosphere for most of it. At the beginning, there were some maybe initial tensions, but we really quickly realized that we need to work together. And we worked very nicely towards the report, finalizing the report, and also setting the priorities. Let me just briefly flash the priorities, and I will develop the subject a bit later. So first of all, the first priority that was, or recommendation, was that the priority of direct searches for dark matter should be the highest, because it's the direct way, the best way to detect the dark matter, and in an unambiguous way. Second, a diversified approach is needed. We simply don't know what the dark matter is. Third, the priority of WIMP searches down to so-called neutrino floor should be given, and I'll explain what that means. Then fourth and fifth relate to R&D and hardware and infrastructure. So, in particular, recommendation 5 was to create a new European laboratory on underground science, and I'll talk about it as well. I'll skim through Axions, ALPs, because I'm assuming maybe this community is not that particularly interested. I'll still cover it. And finally, theory should be given continuation of strong and diverse theoretical support. So this were the main recommendations in a nutshell. Now, let me go to the main part of my talk. I'll give a brief introduction covering the evidence for dark matter. I'm assuming the subject is pretty much well known, so I will not be very detailed here. And if you have questions, please don't hesitate to ask me, but I don't think I should be wasting your time on something that you know. Then I'll talk about what the dark matter is, and I will focus on WIMPs and Axions, mostly WIMPs. I'll talk about direct detection of WIMP dark matter, also again from the perspective of the interest of this of the group at CIEMAT. I'll talk about the current status. I'll talk about the crisis in the WIMP dark matter that has been claimed, of the WIMP dark matter. I'll talk about future prospects for European and beyond searches. I'll talk about the impact of muon G-2 anomaly on supersymmetry, and I'll summarize. Okay, so very briefly in terms of an introduction, we know that there is much more out there that meets the eye briefly, that basically the dark side of the universe dominates the mass energy density, and the WIMP and Axion are the best candidates, the most attractive candidates, but we haven't discovered them yet. So we know that there's plenty of evidence for the existence of dark matter, starting from a coma cluster that was examined by Zwicky in the 30s, where member galaxies move too fast to be explained by visible matter. We know that spiral galaxies show basically flat curves, and luminous matter would only predict a fall off. We know that bullet cluster shows a lot of in clusters. This gas is hotter than then again it would be implied by visible matter. Gravitational lensing arcs that you can see here are caused by more matter than is visible. Bullet cluster is a beautiful example where matter, dark matter, or visible matter and dark matter got dislocated from each other because dark matter passed through each other and baryonic matter got, baryonic clouds are left behind. And finally, CMB, cosmic microwave background radiation, is a very detailed measurement, shows that you need about 25–30% of dark matter, which is much more than baryonic matter, which is all presented in this pie chart. And basically, we can summarize it so that dark matter is felt gravitationally, but not seen through direct or indirect, but other interactions. So the aim is to discover. Before I go into those experimental questions, let me pose those questions that are often forgotten, worth keeping in mind. Is the dark matter a particle or not? Well, it's likely to be, very likely to be a particle. It's nearly a paradigm, but there are still other possibilities that people consider. And even primordial black holes would not be real particles. Something the subject has come back recently. Is there only one species or more? I mean, there could be Axion and WIMP, neutrino WIMP, for example. Still perfectly possible. Is there one type or more than one type? Say cold and warm, cold and a bit of hot, cold and a bit of warm, right? For example. Where did it come from in the first place? Can we explain it in some sort of theory? Can we explain its density? So that's for theorists. Is it connected to the Higgs boson that has been discovered at the Large Hadron Collider? I believe that in the most attractive scenarios it is. Can one detect it? And why is it there in the first place? Who ordered it? So there are many questions that we often forget about. Well, there are even more questions. As this cartoon shows, the people ask, what is dark matter and where is dark matter? But nobody would ask, how is dark matter? The psychologist. So there are many questions that people ask and don't ask, even those that people don't ask. Now, regarding mass range, well, the mass range is enormous, reaching up to 50 orders of magnitude. You can see it here, down here, from, so if this is the scale of an electroweak scale, 100 GeV, and this is 1 EV, then you can go down to the Planck scale, talking about particle physics, but then even, as I said, primordial black holes that are heavier. Or you can go to lighter dark matter, sterile neutrinos, axions, ultralight bosons, down to fuzzy dark matter, where the Broglie when the wavelength becomes larger or comparable with the size of the galaxy, it makes no sense to talk about particles. Interaction range is again enormous, from electroweak down, or even strong, some people argue, to gravitational. So the starting point is not very promising. So another thing is, what is dark matter? There's plenty of the theoretical activities if you follow the literature and the archives, for example. But I think, again, from the experimentalist point of view, there are two prime classes of candidates: WIMPs, weakly interacting massive particles, and Axion, so Axion-like particles, ALPs. And why so? Because candidates in both classes are very strongly motivated by theory, they are discoverable and calculable. You can calculate predictions, you can calculate cross-sections, that's very important. And they've not been invented to solve the dark matter problem. They've been predicted for some other reason, and they come out to be excellent dark matter candidates. The WIMP is predicted mainly beyond the standard model frameworks. The Axion is a byproduct of the Pesce-Queen solution to the strong CB problem with the standard model. When we started working on the report, one of the first questions that we had to resolve is, what is actually the WIMP? What do we mean by the WIMP? Remember, the body of several theorists and experimentalists had different opinions possible. So to many dark matter theorists, if you just walked along the corridor of CIEMAT and asked theorists or autonoma, what is the dark matter? What is the WIMP? They would say, well, it's some cosmic relic with the right relic density. But then more specifically, they would probably say, well, it's a standard thermal WIMP produced from freeze out, in the early universe, freezes out, with a mass of a few GeV to a few TeV, with interactions fixed by sub-electroweak, something fixed by electroweak interactions, but sometimes some mixing angles, so suppressed. But basically electroweak times a factor. Well, this is one point of view. It's a standard thermal view, WIMP sort of hypothesis that has been around for decades, since the 80s, 90s. But about a few years ago, 10 years ago or so, some people pointed out that actually you can talk about a more general thermal WIMP, where you don't need to link its interactions to electroweak interactions. It can be down much weaker, down to even gravitational, in which case the mass would be much smaller, down to EV. Or it could be stronger interactions up to sort of unitarity bound, and then your mass could be up to 100 TeV. So that enlarges the mass range enormously. Then, again, about few decades ago or so, the history is a bit complicated. People pointed out that there are other ways of producing WIMPs in a non-thermal way, so-called freeze-in. It's amusing because a group of people that gave the name to it sort of dominated the citation list, and in everybody's mind is them who introduced it. But actually, the notion of freeze-in was there from the 80s. We had a couple of papers in the 90s on Axion production through freeze-in, but that's for theorists. You invent a nice acronym and you collect citations. I'm not trying to downplay the importance of that paper, but the mechanism was known before. So anyway, in any case, this non-thermal, as they call it, or freeze-in produced WIMP, which is often called feebly interacting dark matter, FIMP, can have mass, again, from EV down on the low scale up to 100 TeV on the large scale. And usually its interactions with the detector are much lower than for the thermal WIMP. But it's a WIMP. It's a general WIMP. So you can see here that standard thermal WIMP of a few GeV to a few hundred to a few TeV is actually a very well motivated, very attractive possibility. But more generally, have a general thermal WIMP, of which you have several other possibilities like stellar neutrinos, asymmetric dark matter. And you can also have non-thermal WIMP, which encompasses a similar mass range. So for the purpose of the report, we've taken the basically pragmatic view that the WIMP is a theory WIMP-like particle that can be searched for in underground detectors. So that's how we decided to define the WIMP, taking the view that experimental dark matter researchers should be inspired but not limited by theory. I mentioned, so I'll talk about WIMP's crisis later because some people made a big fuss about it. Now, where is the dark matter WIMP? That's a question that is very important. We know it's not in the standard model. It provides one of the key arguments for new physics beyond the standard model. But where is it? A few years ago, before the LHC, there seemed to be there was a clear paradigm that the leading candidate for beyond the standard model of physics was supersymmetry. By the way, it still is, but to me, but not to everybody, maybe, but to many theorists, it still is. But clearly, there was a paradigm. Everybody expected, or nearly everybody expected, supersymmetry to be discovered at the LHC. Again, not me, but nearly everyone. And now we know standard model. So we don't know what is the new physics. All the data points towards the standard model, except maybe for G-2. So there's no convincing hint for any direction. How does this imply? What does this imply for dark matter? Again, a decade ago or so, people talked mostly about SUSY WIMP and neutralino. These days, we don't know. I mean, there are many possibilities, again, with the neutralino remaining one of the front runners, clearly. So, from the point of the report, and in particular, planning searches for the next decade and beyond, one of the key questions we had to raise was, or face, was, should we abandon standard WIMP searches in the mass range of a few GeV to a few TeV that most of the experiments, or many experiments, focused on in preparing, in running, and also in preparing new generations of experiments. And then, very recently, what is the impact of the new mu on G-2 anomaly that was around before, but now it was confirmed, the measurement. So more sort of generally, this is the mass range, right, up to, for particle dark matter, general thermal WIMP from EV scale to over 100 TeV scale, 100 TeV, with some interesting candidates that some people favor, some theorists, for example. And then there is also the Axion side, where the Axion is typically much lighter. The classical QCD Axion is in this mass range of a few mu EV to a few MeV. But again, like with the case of in the case of WIMP, you can take a more general view of the Axion that can be much lighter or even somewhat heavier. Sometimes it's especially on the heavier side, it's not dominant dark matter, it's subdominant. So this is the big picture. So the recommendation, the first recommendation we made was the following. The search for dark matter with the aim of detecting a direct signal with detector should be given top priority in astroparticle physics because a positive measurement will provide the most unambiguous confirmation of the particle nature of dark matter in the universe. Why? Because any other method, I'll mention them a bit later, would not make it unambiguous. Indirect detection would not make it unambiguous. There will be always question whether it's not an effect of some astrophysical effect, and in the collider, we'll never know it's dark matter or it's just some sort of semi-stable particle. And the second recommendation was that we need to take a diversified approach to cover the broadest possible range because we simply don't know where it is. So in the case of thermal WIMP, non-thermal WIMP, or Axion, look wherever we can, but sensibly, using the means that we have, the tools that we have, and the funding that we have. So dark matter detection, I mentioned that direct detection is one way. You scatter a dark matter of a standard model particle in some target, but you can produce them in a halo, for example, and then look for say exotic particles like antiprotons or positrons and so on. A clear signature, but then there are astrophysical effects. So you can produce them in colliders, and you don't know they are really dark matter. So focusing on direct detection, there's an impressive array of techniques, starting from scintillating crystals like sodium iodine. Basically, you scatter off a web from the target. Bolometers, we use phonons, liquid noble gas, either single phase or double phase, which is, for example, what dark side does. And then you have a matter of discrimination with liquid noble gases like argon or xenon, or you can use a bubble chamber. Again, no discrimination, or in development, directional detectors, gaseous directional detectors are being developed. Now somewhat behind, but a very interesting development. So what is the current situation? On the left-hand side, we have listed all the experiments that are running in the world. This is a world picture, or are in preparation. And you can see, I mean, you'll be in each category, cryogenic, liquid xenon, liquid argon, they are running and so on. They are liquid, they are running and experiments in preparation, except the dark side. I'm not sure the date is still valid. And then an ultimate Argo experiment that would have 400 tons of liquid argon, or on the xenon side, Darwin with 40 tons. Again, it was a somewhat, I think, optimistic timescale. And then there are more experiments. And we've listed sensitivity, but I think it's easier probably to see the sensitivity in the figure where I show WIMP mass versus direct detection scattering cross-section elastic. And you can see that the leading experiments now are the experiments with liquid noble gases, liquid xenon. Panda X is a Chinese experiment, and also liquid argon with 50 kilometers. And deep, bolometers are somewhat behind currently, but they are actually quite sensitive at lower masses. Although at low masses, so dark side and xenon showed with special techniques that they developed, they became more sensitive to lower mass, even though their sort of main target coming from the mass number is based on the mass number is at larger masses. Now you can see here there's neutrino, so-called neutrino flow of coherent interactions of solar and atmospheric neutrinos, solar and atmospheric, and the push has been so far to reach down to the neutrino floor on the heavy mass side, and on the lower mass side, those techniques provided by allowed xenon and dark side to become more sensitive to lower masses. Now, one of the first questions we had to ask was whether we should continue, or they should continue pushing in this direction, or abandon this and go somewhere else, like the US. In the US, there's a big push to go into sub MEV scale, so down here and even below mass range. So we decided that the thing to do is for the community, to recommend to the community, is to go down as quickly as possible to the neutrino floor on the higher mass, atmospheric neutrino floor, and also to push towards lower masses to reach down to neutrino floor on the solar side. Why so? Because there is this will have enormous impact. This discovery will have enormous impact, not only on the field, obviously discovering dark matter, but also on the collider program, for example. If a massive particle is discovered, say 100 GeV scale, a few hundred GeV scale, that would be a very clear indication that there is really new physics at that scale. Or my claim is that new physics is at the few TeV scale. So that would give a very, very strong support to building new colliders. Without that, how can we argue with politicians to give us enormous amounts of money? So this has impact, will have impact not only on the dark matter community, not only on astroparticle physics, but also on collider physics, experimental, and also obviously on theory and model building and so on. So we decided that it's worth keeping the effort of pushing down and pushing towards lower masses, see if there is indeed new physics there. But some may say, wait a second, the WIMP is dead. The WIMP is dead. It's been announced to be dead. A few years ago, actually, somewhere like after the LHC, after the first run or two runs, failed to find supersymmetry or any sign of new physics, many people started arguing that basically dark matter is dead and new physics, supersymmetry is dead. So let's have a closer look at this, a scientific look. What are the main arguments raised against thermal WIMP as dark matter? Searches have been going on for so long with zero non-results. And second, most of the, in quotes, allowed cross-section ranges have been ruled out, but only small remaining window left. That's how you would sort of generally hear it. I've had a number of conversations with, say, policymakers, directors, who sort of get it at that level. Let's have a closer look. Is the WIMP hypothesis already dead? What was the standard WIMP with a few GeV to a few TeV mass range? In this standard WIMP hypothesis, the Ricks abundance is linked inversely proportionally to the annihilation cross-section in the early universe. Particles annihilate, produce WIMPs, and at some point they cannot meet each other anymore, and WIMPs freezes up. And then, in order to get the right Ricks abundance, omega h square, I'm sorry, sigma times v, Lessing cross-section relative velocity, should be 3 times 10 minus 26 centimeters cubed per second, and that's a weak interaction cross-section. And that's a natural target for indirect detection, where you annihilate the dark matter particles into standard model particles. And this is how it will be searched for at CTA, how it's been searched at HES, and so on. And there they have a target that they need to go down to. They are somewhere here, and they will go down to below the thermal target. If they find nothing, you can say that they've reached the target, they've eliminated the possibility. Even though there are still large astrophysical uncertainty, scalar profiles are unknown. If it is flat, it will be harder to get to that level. The galactic center and foreground are big unknowns, and so on, the size and distribution of clouds. But generally, if one goes, say, an order of magnitude below the thermal target, one can say that the WIMP hypothesis is in trouble. This has not happened yet on the indirect detection side. But the question is there another analogous benchmark for cross-section for direct detection? And the answer is no. That's very important. The predictions that my colleagues and myself have been doing for decades are model dependent. The lower limits depend on theoretical expectations, assumptions, are known to have blind spots. So there are still unexplored ranges of correction sections which are a priori as probable as already excluded ones. So when we show various predictions, remember that predictions are subject to all those limitations that I mentioned. So you can have predictions here, you can have predictions here, you can have predictions even below the neutrino flow, unfortunately. The answer is that simply there is no firm solid prediction that one can point and point out and eliminate. So therefore, claims that thermal dark matter have been disfavored because most of the parameter space has been ruled out are simply unfounded. They lack scientific basis. They're not even maybe slightly ruled out. They are, but not. There are lessons to learn from other searches. Higgs boson search at the LHC, remember 9 years ago, when LHC eliminated most of the mass ranges, some people started panicking. Papers started being written about no Higgs anymore. Instead, Higgs was discovered in a tiny 15 GeV window, actually predicted by supersymmetry, which is there. Gravitational waves were searched for nearly 40 years before they were found. So dark matter searches have been going on for 30 few years. Still have a few years to go. Don't panic. There is no need to panic. Okay, so the target is to reach down to the neutrino floor at higher mass and also at the lower mass and complete it rather than panic. So what is the current situation and what is the situation in the future that will be reached in the future, hope? So this is the present situation I've shown already. And for comparison, a bit different scale here, right? Minus 39 here. So this is the current limit. And the new generation of experiments that is being prepared, Panda X and LZ and Xenon and Tone, which are actually being commissioned, they should be running within a year or so, should reach straight down to respective, maybe half of the parameter space, an order of magnitude or so, maybe even more below the current limit. But they will still remain about an order of magnitude to reach. And for this, you will need much larger detectors like dark side with 20 tone of a liquid argon, and argon and Darwin on the liquid xenon. So that's a large mass. At low mass, bolometers are hopefully going to reach down to close to the neutrino floor. They are hoping to reach down to the neutrino floor, but it's going to be a challenge. So this will be a challenge for them as well to hit the neutrino floor at this mass range. This will be an achievement in itself. And then Cygnus is an indirect detection, not indirect, directional detector, and is for the future. So we'll eventually have a chance to reach down. So the recommendation 3 was the experimental underground program should, with the best sensitivity, should be given the highest priority to go down to the neutrino floor, down here at larger mass, and try to hit the neutrino floor at the low mass, the solid neutrino floor. It should be given enhanced support because A, it will be an achievement in itself, amid immense competition, and B, it will have enormous impact on particle physics, including collider physics. Now, what about beyond leading efforts like sodium iodide detectors or directional detectors, or covering lower masses? Should they be abandoned? No, they are very important. For example, we still don't want to know what the Dama Libra claim is. Second, directional detectors, once the WIMP is discovered, if it is discovered, directional detectors will be key in actually confirming that its halo origin and so on. So lots of R&D needs to be done, pushed, even though those experiments do not guarantee much far behind in sort of having a chance of discovering a WIMP from the standard point of view, module surprise, of course, than the liquid noble gas or bolometers. Liquid noble gas or bolometers that should be even enhanced. So R&D and efforts on those other directions should carry on. Now, the next recommendation had to do with European underground laboratories. I'll go through it rather quickly, but the fact is that European laboratories, we have a few. We have obviously Gran Sasso, we have Modan, we have Canfranc, and also Bolby. And they are not very deep, but altogether they provide a respectable, especially Modan, respectable environment. Problems with them that they are national laboratories. More and more they are national. That's a problem for them from the point of view of funding and cooperation. And the idea that we had, not on us actually as it came out, was to form a European laboratory that would be based on those existing laboratories, but it would be geographically located in different locations, but it would be run as a single laboratory. So taking an example of CERN, but applying it to astroparticle physics and generally underground and seismic physics. So the idea was to create a distributed geographically, but integrated from the point of organization and funding, structure of underground laboratories for the needs of the forthcoming generation of new experiments, not only in particle physics, not only in astroparticle physics, but actually biology, seismicity, and so on. So we recommended to create a European laboratory for underground science, knowing that it's not going to be easy, but surprisingly enough, it's taking some interest. Now, very briefly on Axions, because time is running. Axions is a very attractive candidate, Axion, and also more generally ALP-like, Axion-like particles. There are different search techniques, halo scopes, looking for axions in the halo, or looking for axions produced in the sun, helioscopes, or looking for axions produced in the laboratory. And also low background WIMP experiments can look for axions which are sort of KeV scale, so subdominant as dark matter, but could be there, who knows. So I will just skim that these are very important searches, and the recommendation has been to continue them and to focus on European windows of opportunity, which are outside of the sort of main windows dominated, where the competition is very intense, and where the US and Korean experiments are far far ahead, and very hard to compete with them. Now, to summarize the report and the recommendations in particular, first recommendation was to give highest priority to direct search for dark matter, because that would provide the most unambiguous way of discovering dark matter. So there will be an update in the APEC roadmap that was created a few years ago with that respect, and also to establish a global forum for relevant funding bodies and experiments talking to each other, so that there is some cooperation and coordination. The whole search is becoming not even sort of European or global. A diversified approach is still needed because we don't know what the dark matter is. Priority for WIMP searches down to neutrino floor should be highest, because there are important arguments, scientific arguments. The WIMP is not dead, definitely, and it indeed would play a very important role to reach down, impact to reach down and find if there is really new physics at the GeV or 100 GeV or TeV scale. For European R&D, we recommended very strong European level R&D, coordinated, just like it is done in particle physics, in collider physics. And also to create a European laboratory for underground science. It's challenging, but needed for the future of European underground science, not only physics. The Axion ALP searches should carry on, with the Europeans focusing on the mass ranges where Europe can be competitive. And finally, theory is strong in Europe. It's very diverse, and so support should continue, and perhaps some coordination should be given to UCAPT. So it's a center that was created at CERN with the blessing of actually by APEC and the other sort of meeting communities that carry on. Okay, so that's about the report. And now I don't know how much more time, if any, I have.
Yeah, go ahead. Don't worry.
Right. So I will just maybe finish the talk, and then if there are any questions, we can talk about everything together.
Yes, I think questions at the end is better.
Okay, good. All right, so as everybody knows, last when was it? End of March, right? Towards the end of March, Fermilab U1G-2 experiment announced its very long, very much awaited measurement. And together with the previous Brookhaven experiment, they found 4.2 sigma deviation from the standard model calculation. And so that's, in some sense, a big surprise. In some sense, a confirmation, depending on the point of view. It's the only remaining sign of new physics pointing towards lower energy range, lower mass range, 100 GeV or so. Everything else has evaporated. Flavor physics is not showing any convincing deviations at the LHC. Direct searches, we know, limits are for electrowickinos are in a few hundred GeV mass range, and for strongly interacting particles in a few TeV range now. So even the Higgs boson mass, in the case of supersymmetry, points towards stop masses that provide loops that provide radiative contributions to the Higgs mass in a few TeV range, basically. So everything is pointing towards, if any new physics, it's at the TeV scale, a few TeV scale, My favorite range is few TeV to about 10 TeV from the Higgs mass point of view. So this is the only measurement that has been confirmed that points towards new physics at the really electroweak scale, a few hundred GeV. There's a recent review, 100 plus pages, that was shown, that was published a few days after the announcement. However, it's worth remembering that on the theory side, the situation is less than fully clear. We know it's a very difficult determination. And in particular, a paper appeared in Nature on leading hadronic contribution to the muon to G-2 from lattice QCD, which shows no need for new physics. It's only slightly different from experiment. So I will ignore this, like basically most of the community, because we are thirsty of new physics. But let's remember that the paper in Nature is a paper in Nature, should not be ignored. And it shows basically a result from them is somewhere here. Again, if it's so, then it would, the need for new physics would evaporate. Okay, so there was a flurry of papers, obviously, right after the announcement, and we produced our paper as well. We looked at it from the point of view of unified supersymmetric models. In the general supersymmetric scenario, it's very easy to generate large enough contributions from SMU and neutrino or Georgino and Wino, because I'm sorry, SMU and neutrino or neutrino mu. SMU1 because basically masses are free parameters. You can always adjust them to the few hundred GeV scale to get the right contribution. Now, supersymmetry without ground unification is interesting, but to a theorist, it lacks real motivation, because why invoke supersymmetry if there is no hierarchy problem, if there is no ground unification of couplings and masses? So we looked at the situation from the unified SUSY point of view, and there the situation is much harder, because there electroweakino masses are linked, first of all, interrelated to each other and linked to strongly interacting masses and to unified masses. So there it's much harder to get the right contribution. And indeed, in the simplest scenarios, like the constrained MSSM, where you take the common scalar mass, common gaugino mass, common trilinear parameter and tangent beta, or the non-unified Higgs mass, where you disunify the Higgs masses, soft Higgs masses from the M0 parameter, like quarks, lepton. In those two scenarios, you cannot reach up to the required discrepancy. You cannot generate big enough contributions. If the red tower is for the Rayleigh abundance being consistent with the current, with the density, or even if you make it subdominant, you can only go up higher but not reach the desired values. However, in models with non-unified gaugino masses, where the masses of the gauginos, Wino, Bino, and Gluino, are not unified, taking simpler scenarios of only Bino and gaugino and Wino mass being unified or being disunified altogether, or taking more specific GAT group, gauge group inspired models like SO10 or SU5, where there are more free parameters, but gaugino, non-unified gaugino is key here. You can easily get to the right level. So that's a very important lesson, right? If this is confirmed, then unified SUSY can only be realized with, or mostly with non-unified gaugino. What does this imply for dark matter? It's interesting, it's very important, because so I said, the lower, because you have loop contributions to G-2, this is the difference, the required difference. This is the mass, the neutralino. So this is the non-unified gaugino mass. One model where Bino and Wino are unified, for example. And generally you see that, of course, the contribution drops down with mass because you have a loop contribution. But at the right range, you can only have BINO-like dark matter, BINO-dominated. Higgs-ZINO, where the rate abundance is at least 1 TeV or more, cannot contribute to the anomaly if you require the right amount of dark matter. If you allow for subdominant dark matter, then also the Higgs-ZINO and the WINO can become much lighter because the mass is linked to the abundance is linked to the mass, basically like a parabola. So you can have also much lighter subdominant WINO and Higgs-ZINO, and with the low mass, a few hundred GeV, so less than 340 more or less. You can play with this a bit, but it's subdominant. Now you can see this here. The Rake abundance is large enough only for the BINO, for the sort of beige and red points, which are Higgs-ZINO and WINO. It's across the subdominant. It's only for the gray points, which is a BINO, which is subdominant. If you allow for subdominant dark matter, you can have a Higgs-ZINO and a WIMP. What does this imply for dark matter searches? So these are all the points that were shown, but the points with the right Rake abundance and there is the BINO are here, and they have very strongly suppressed cross section. The cross section is very strongly suppressed. It will be very hard to reach down to with the current range of experiments being prepared. One would have to wait for the next generation. They're close to the neutrino flow. For the BINO, Higgs-ZINO or WINO, the cross sections are respectively higher. They will be searched for with the experiments that are being commissioned, but they imply strongly subdominant dark matter. So it's an interesting situation that is developing. In this context, dark matter would be subdominant if it is found at low mass by the current generation of experiments that we running within a year or two. Okay, so this is an interesting situation that obviously has an impact. But we have to remember about this paper in Nature that says that perhaps this range is not really there. That actually is much lower. It could be somewhere here. So to take home, evidence for dark matter is convincing, but the nature of dark matter is unknown. There are many candidates, but a few are well motivated. But even if those few well motivated ones is very hard to search for, although not impossible. Actually, I think the program is very promising. Generalized WIMP, experimentalists, WIMP and Axion candidates are still front runners. I think are strong front runners. Direct detection in Europe is very strong. Experimental programs is very impressive, and also in worldwide with strong competition, especially from China on the WIMP side. And there's a high chance of success, and it's the best way to go to discover dark matter. Situation with G-2 remains unsettled. If the anomaly is confirmed, I mean the difference, also on the standard model side, the calculation, it will imply a fairly light dark matter, and possibly, if it is discovered within a year or two, subdominant. That will imply probably supersymmetry. So, predicting the future, what can we say? Obviously, one firm thing you can say is that we need a genuine WIMP signal with more than one dark matter search experiments. That's for sure that we can say about the future. Thank you.
Thank you very much, Leszek, for this very comprehensive talk and overview, and for raising our hopes up for direct detection, which is always something that I think the community needs Okay, so I see already a couple of raised hands. Adrian,
Okay.
go ahead.
Thank you very much for your nice talk. I would like to ask you a question concerning the how much are you taking into account the simulation of the cosmology and stellar evolution in order to constrain such a huge space parameter like those of axion light particles and WIMPs? I mean, are you taking into account most recent non-standard cooling effects, galaxy clusters dynamics in order to try to put constraints in the search of the dark matter on experiments, taking into account that these constraints can reduce the possibilities of the space parameter?
I'm not quite sure what space parameter you're talking about, because you might have noticed I actually, as a theorist, didn't show any theoretical prediction, any scatter points showing regarding dark matter, other than the last part of the talk. There are just theoretical predictions coming, which have nothing to do with what you said, but the only input that comes is, and actually this is on the experimental side, is the local density of dark matter. The local density of dark matter, and that's determined by a number of methods, astronomical methods. And obviously the situation is still, until the dark matter is discovered, it remains not 100% known, but basically there's a convergence on the local density being at the level of 4 GeV per centimeter cube, not even 0.3, that is a standard value that is normally used, but 0.4. There's a new review coming. I think it's already on the web. It's being
okay.
It's already on the web.
I was thinking about the asymmetric dark matter annihilation inside some stars close to the halo region, because there are some papers that claim that the stellar evolution observables can put constraints on WIMP's properties. So I would like to know if you are taking this feedback in order to try to address the search or for the WIMPs.
No. We're talking about basically, a WIMP has to arrive in the detector. So we're talking about the local density. The local density. Any additional production modes can only increase the density. The density may not be uniform, because the local doesn't mean at the Earth location, but at the sun's location. And we could be living in an overdense region, but we might be unlucky and be living in an underdense region. This we don't know. It's unlikely that we live in an underdense region, but who knows? Generally, people assume that the halo is fairly smooth with some overdense regions.
Okay, thank you so much.
Adrian, if you don't mind muting yourself. Thank you for the question. Thanks. Roberto, I think, has a question.
Thank you, Leszek, for this nice talk. I mean, in several occasions, I expressed my my opinion that Leszek, I think, is one of the few in our field who is able really to speak a general language, which is that can be understood by both theorists and experimentalists. So let me come to the question. I have actually two questions. The first one is if you can comment a bit more on non-particle explanation of dark matter. For instance, you know very well that primordial black hole is a hot topic, and especially in Spain is a very important topic. So I would like to hear your opinion about this. Are they ruled out? Is still a possibility? And then the second question, maybe a little bit more general, if you can comment a bit more about this idea, one of the recommendations that you mentioned, this idea of this new international lab, as far as I understood, what could be the strategy, for example, to get there? This is an idea of a new deeper lab, which is time to time discussed, but how to get there in this field? Is it really possible to have a new lab having this fragmentation in the field? What could be the strategy?
Thank you, Roberto, and also thank you for your nice words. It's always a pleasure to talk to experimentalists. It's always surprised that experimentalists still want to listen to theorists who have been promising new physics all around, just around the corner. Remember what I said at the beginning. I never claimed. Actually, I was being cautious about claims that very cautious about claims that LHC would find dark matter, new physics, supersymmetry. Anyway, so regarding primordial black holes, it's an interesting possibility, obviously, and it's not closed as a window. We know that black holes exist, primordial black holes, even though there are many questions about their production in the early universe, are likely to be there. And I didn't prepare a slide, unfortunately, but there is a window, some people claim even 2 windows left, which is still possible. And, we have to live with it. What can we say? I can refer you to, sort of, I don't know, 70 or 80 page review of Bernard Carr and Junichi Yokoyama and others. So, the size of the report tells you that the story is unsettled. But is there? It's a possibility. It's not my favorite candidate. I believe strongly in the need for new physics in particle physics. Because of the theoretical issues of the standard model, related to the standard model. The standard model clearly is not the end of the story. There are so many unknown parameters. It's a whole great group. It's just the Higgs mechanism is just putting by hand all those things, but it's not guaranteed. It's just a very, very attractive possibility. You have to remember this, and there's nothing new to say, right? So don't lose your hopes. We have a competitor, but it doesn't invalidate anything that you've been doing so far in terms of searching for WIMPs. Regarding the underground lab, so the situation, as you in Spain know it better than anybody else. Canfranc is an interesting setup, but attracting experiments is not easy. Attracting funding is not easy. It's a bit of a struggle. It's not a struggle of only Canfranc, but also I'm hoping I'm not saying anything, sort of politically incorrect or troublesome. It's the same with the UK. It's the same with even with certainly Modern. It's the same with even Grand SAS. Now we have to look into the future, and how can we make use of European laboratories? Can we twist it so that actually not having a deep enough lab site, can we make the best out of what we have? So what we can make very best of is to suddenly integrate the running. I will not go into a lot of details of this because, for example, uniformize the standards that are used in different laboratories. Try to have some common policies. Attract more funding. How can you attract more funding? If I take, say, Polish government, some other country's government, how can we convince a local government to invest more money into an underground lab other than the money that goes through experiments that run there? However, if we could think of creating a network of underground laboratories, including some other laboratories, which obviously are not deep enough to be sites for dark matter searches. but have other fantastic properties. Like in Poland, there is a more shallower site, but it's very, very radio pure. It can be used as a supporting laboratory for R&D. If you can create a program, a European program of R&D, and common sort of program of collecting signals not only from dark matter search, but also from, say, biology, seismic studies, creating a network of laboratories, then I would imagine that national governments would be more willing to support this, because they would have more communities would have something out of it, and possibly even national laboratories, which have no chance of competing with those big ones, would also be part of the picture. So these are interesting possibilities that are worth exploring. And interestingly enough, at the upper General Assembly level, this recommendation, and not only at General Assembly level, but also the level of directors' labs, this has really taken track, has been shown a lot of interest, and there will be hopefully a committee created to look more into this in more detail. So the story is being explored. I will see what happens. Now, about means of how can this be achieved? There are European programs for creating infrastructures, providing funding that can be explored. And we'll see if this cannot be perhaps used towards achieving this. So we'll look for this possibility, creating an integrated structure using European funding and contribution from national governments. We know it's not going to be easy, but there seems to be quite a lot of determination in this respect.
Thank you.
Okay, any more questions? I have a very quick one just to understand this, the time scales. When you were talking about the push towards lowering to the neutrino floor for new experiments, you listed a series of experiments or future limits there, just bordering the neutrino floor at the GeV-TeV scale. What is the question is, what is the time scale for those experiments to reach that floor right as it stands right now?
Well,
just
the current the experiments that are being currently commissioned, I can say, LZ, xenon and tone. I should have mentioned LZ, a very interesting liquid xenon experiment, UK mostly, and in the US. Panda X for tone and xenon and tone, they should be there within, I don't know, Roberto will love, or maybe you, something like, a year or two.
Oh, okay.
But then going down for another decade in the cross section would take, and then dark side with 20K, say within the next half a decade in time, which go down another half a decade in the cross section.
Mm-hmm.
But then to reach down to the neutrino floor, you need to increase the size by a factor of 10.
Mm-hmm.
And that's because you will be talking about, one event per tone per 100 years or something. So you need to increase the volume. And we know that both argon and xenon experiments can be scaled up easily.
Mm-hmm.
In quotes, easily, of course, but easily, much more easily than any other setups. So it's a matter of building big volume. So about Darwin and Argo, my take is we're talking about the next decade plus.
Mm-hmm.
So it's a long, sort of scale. On the other hand,
Yes, I guess I was just trying to wrap my head around when the next decision point is going to happen. When, let's say, imagine pessimistically that nothing is found. Just understanding this is going to happen in the next 10 years or 20 or so.
I think if nothing is found, where? If nothing is found at the Large Hadron Collider, I don't think it should affect dark matter searches, because there, first of all, you can take the sort of experimental view that theory and experiment are related, or loosely related in terms of motivation. So I would not expect, honestly, sorry to collider experiments. I would be very nicely surprised, but not putting much hopes into the next run of the LHC. I'm putting much bigger hopes into the high luminosity run, although again, not full hopes. The best chance is really to explore where the WIMP in the few hundred GeV to a few TeV mass range is there. If it is there, that will raise everybody's hopes, because it will tell us that the new scale is at that scale, new scale of physics, the understandable is there. If nothing is found, then it will be really, really difficult for us to argue for experimentalists to argue for new money. But I'm fully convinced that the best way, and in some sense the safest way, is to actually push down with direct detection in this mass range, because that's the oops, I'm going too far. That's the best. That's sort of the, given the theoretical, the experimental setups and the momentum and the funding and the expertise, rather than abandon this and go somewhere else, like what the US seems to be planning to do, or at least this push there. Explore this down to the neutrino floor and see, it is there or is it not there? If it is there, great. If it is not there, well, life, right? Remember, the LZ experiment is, they get current funding. They said we cannot get any promise of new funding. If we find nothing, we may not be funded anymore. In Europe, the recommendation has been, even if nothing is found, if LZ or xenon and tone or Panda X for tone, carry on, go down to the neutrino floor. That's the recommendation, and we'll see. I mean, we need to close the hypothesis, explore the hypothesis. If it is there, great. If it is not there, tough luck. But we need to leave some physics, to do some physics to our grandchildren, right?
Okay, and I think that's a great bottom line, and to finish this seminar. Thanks everyone for sticking till the end, and again, thank you, Leszek, for joining us for this last seminar of the season, and hopefully we'll have you on physically at some time in the future at CIEMAT.
It will be my pleasure.
Okay.
I hope so too. Okay, thank you. Thank you for the invitation.
Okay, thank you all. Bye-bye.
Thank you.
Thank you for the talk. Yeah. Bye-bye.